This is examples class 10, example 3b. So we're following on from example 3 here to look at a confidence interval for that paired test that we just did in example 3. So in example 3, we decided to use an alpha value of 0.05. It wasn't specified, but we would specify that 0.05. And we were testing a hypothesis which was about difference in blood pressure to see if the mean blood pressure while waiting for the dentist was higher. So we had a one-tailed test there. So we had a one-tailed test which put all of our alpha value at the one end of the distribution. Now, if we're doing a paired sample t-test, we have a related confidence interval. And that confidence interval would look like mean difference plus or minus alpha value, critical t value multiplied by standard error. So mean difference plus or minus critical t multiplied by standard error. And recall that when we have a confidence interval, our decision here is to find out whether 0 for the mean difference lies in the confidence interval or not. Now, in our example, we had used an alpha value of 0.05, and it was a one-sided test. So 0.05 at the top end of our distribution gave us a critical t value of 1.833. Now, a confidence interval must be a symmetrical confidence interval. So 0 in the middle of our distribution here means that to find the confidence interval using that same critical value, we'd have to put the same critical value on the left-hand end, minus 1.833, corresponding to a left-hand area in the tail of 0.05, which of course leaves us with 0.9 inside of those two positions, which would give us a corresponding 90% confidence interval. So this would be a 90% confidence interval if we used that same critical t value. So 90% confidence interval, symmetrical about those 2 points. And again, we're looking to see if 0 for mean difference of 0 lies inside of that confidence interval. So the calculations that we had for this to work in with our confidence interval, we had a mean difference of 5.7. We worked out the standard deviation from the square of the standard deviation, the variance formula, and we calculated the standard error by standard deviation, square root of variance, divided by sample size, square rooted. So we had a standard error measure there of 1.9035, and remember we'd got that critical value of t.05 at one end with 9 degrees of freedom of 1.833. So those calculations we've taken from example 3, which we'd previously done. So in order to put those numbers now into our confidence interval calculation, we need 5.7 for the mean difference, plus or minus that same critical t value, 1.833, multiplied by the standard error measure that we had from the previous slide, 1.9035. Now, first thing to do is the multiplication there, 1.833 multiplied by 1.9035, and I've calculated that to 1 decimal place to fit in with the 5.7. So that gives us 3.5. 5.7 plus or minus 3.5, which means that we add 5.7 and 3.5, we have 9.2 at the top end, and we have 5.7 minus 3.5 at the bottom end. So this gives us a confidence interval from 2.2 at the bottom end up to 9.2 at the top end. And remember, this is the 90% confidence interval, 90% confidence interval. So now we have a 90% confidence interval, which you'll notice is all positive from 2.2 to 9.2, meaning 0 is not inside that confidence interval. 0 is further across on the left-hand end of the confidence interval, and this means since 0 does not lie in our confidence interval, that means that we were correct to make the decision to reject the null hypothesis in example 3. So further to our rejection of the null hypothesis, we now have a confidence interval of values that that difference in mean blood pressure could be. So as you're interpreting a mean difference, you're looking for 0 lying in the confidence interval, and if 0 does not lie in the confidence interval, that gives us evidence to suggest it's not a correct value. If 0 does lie in the confidence interval, we have insufficient evidence to reject 0 as a possible difference. And that's the end of our confidence interval calculation.